on Wednesday to repeat quiz similar to this one. Is this the way to resolve it?
Sure.
And I feel a little bad for a few people that did well, and they say, wait a minute, when we did well, it doesn't count.
Yeah.
So what do we do with them? We give them some bonus or keep
Can we
the
trade
score?
in a horrible quiz score?
Yeah.
Yes, please.
Trade it.
Okay.
Yeah.
That's unfair. So, if you like your score today, you can trade it. If it's, no, I'll take that back. If it's 5 or above, you cannot trade 3 for 1. I don't want to do that. So, if your score today is 5 or above, you are allowed to trade it for one of your bad scores on quizzes, but everybody takes quiz on Wednesday. So that I want to be sure that everybody can do this. Okay, so then everything is resolved. Nice. That's what I wanted to tell you about it.
Yeah.
Any questions, any comments? Okay, now then let's go to the homework and then to new section. What's question from home? How did all that look like? Complicated or doable? It's combinatorial principle, and it always be very, very hard. Some research paper sometimes in the middle hole is called pigeonhole principle, but it's not about principle. It's preparing it and seeing all those classes, and then you call it that. So I wanted you to see. Yes.
You want us to pass these up?
Yes, please. Please send me your scores for your solutions for analysis if you want me to count them for that bonus.
Where should we send these scores?
What's it?
Where should we send these scores? To your email?
No, send them to me now physically.
Oh,
Just so that I
okay.
don't go around. So that I can start. Send them ahead. So at the front of the class. Here's the
It matter.
just bring them up. Yes.
Can you manipulate both sides at the same time to show that
That's valid, of course. That's what at least we should know. Study logic.
some professors aren't cool with that?
They're not here about being cool. They are about so, people might get pedagogical reason. I tell you, even in my 3 class, I tell you why.
Yeah.
Because
There's like multiple.
both left and right end up to the duty with some 13. Can you just go this way and reverse the steps, yes or no? So there's always an easy way to do that. So it's not just insisting on some form. There is real pedagogical value in that. But in general, it's absolutely correct if you go and transform both sides. All right, questions from the homework. Are there any?
What do we do with the quizzes if we want to trade them?
If you want to trade the quizzes, give me the instruction on the back,
Okay.
trade for quiz and number, and give them back to me, okay?
Okay.
Questions from the homework, are there any? Oh, there are some, yes, oh,
4.
4, what's there? Oh, 4 is a nice, very elegant problem. Yeah. It's from, I think that problem is, yes, from Edgewood. You can find that there in the list of the problems. Read it. So I have numbers A1 to AN. And they are all less than or equal to 2n. Who's are going to be? We'll, for each of those numbers, we'll pull out the even part. What do I mean? Can I factor out as many 2's as they have? They might have no 2's at all, or they might have, so we do the following. A1 is 2 to the K1 times C1. So what did I do here? I pulled out all the 2's it had, if there are any, and what's left then? When you pull out all the 2's, is that an even number or odd number? So B1 is odd. Then A2 the same way. 2 to the K2, B2, again, B2 is what? numbers do we have here? Let me see, is this n or n? N plus 1 integers, sorry. N plus 1. So there's a n plus 1 is also 2 to the k n plus 1. Bn plus 1 is odd. Let's look at these b's. Are they all odd? Yes or no? Are they all, so b1 to bn plus 1 are odd, and they are less than or equal than 2n minus 1. Because if they are below 2n, which is even, they are less than or equal to 2n minus 1. Let me write all the odds below 1, below 2n minus 1. What are they? 1, who's next? 5, and that depends how big is n. The last one is what? 2n minus 1, which I can write like this, or 2n minus 1. How many numbers is this? Can I count them? The way I wrote them might be easy to count or not, but here's an easier way to count them. 1 is 2 times 1 minus 1, okay? 3 is 2 times 2 minus 1. 2 times 3 minus 1. And it is 2 times n minus 1. So how many numbers is this?
2 to the n.
No. Just counter. Here I used 1. Here I used 2. Here I used 3. Here I used n. So how many times did I do this? N. So, b1 to bn plus 1 all belong to this set. So if I call this set A and this set B, who has more elements, A or B? A has how many elements? Look at those B's. How many of them? How many elements do I have here? The size of A is n plus 1. How much is the size of B? N. Do I have more pigeons or more holes? So what happens? 2 pigeons are in the same hole. What is that meaning? That means that 2 of these B's are equal. So Bi equal Bg. So since there are n plus 1 of them, and they have just n values, 2 of them must have the same value. So why is that solving the problem? So then, how does AI look like? AI looks 2 to the ki bi, and aj looks 2 to the kj bj. Oh, bi, the same one. They use the same odd part. Are these two numbers divisible by one another? Yes or no? Why? Because if they have the same odd part, then divisibility will be decided by who has more what? Twos. So then one of those numbers is bigger than the other. You know, let's say ki is greater than or equal to kj, then ai divided by aj is 2 to the ki minus kj. Their quotient is integer. So it is generally, it's interesting. 2 numbers are divisible by one another if they have actually the same odd part. And then n plus 1 number, among n plus 1 number, there should be 2 of them with the same odd part. And they are then divisible by one another. Which means 2 to the q plus 7 and 2 to the 5 plus 7 is one of the numbers divisible by the other, yes or no? Yes, it's just 4 times bigger, right? So if you have the same odd part, then that guarantees divisibility of the number that has more 2's by a number that has less 2's. And that, so the whole idea in this problem is to reduce, because I have just n plus 1 number, and here 2n, that's too many holes. But when you start talking about odd part, then the list of odd numbers is twice shorter, and then you qualify for bigger holes. So that can. And you can say what? You see, by learning pigeonhole doesn't mean that you will now be able to solve problems with it. It depends on the context of the problem. So it's just more to recognize the technique and then set it down. Next question, maybe one more question before we start with the section. Is it others? Oh, do you know a problem? I don't know how much that qualifies for pigeonhole, but I like that problem a lot. Number 3, if you have a chessboard, you know that one? That's one of the standard puzzles. Eric, can you comment? Problem number 3, there is a chessboard, and then 2 opposite corners, 8 by 8. And there's a whole list of problems of this type in combinatory. You remove 2 opposite corners. The question is, can you cover that board by 2 by 1 dominoes? So here's the domino 2 by 1. Can you somehow line them up and cover the whole board? Looks doable. Why? Because how many fields do you have? 64 minus 2, and that's what? Is 62 divisible by 2? So it looks like 31 dominoes should be able to cover all this. But it's not true. You cannot cover it. Why not? Because sometimes when you keep covering, it will happen that one corner left is here, one corner is here, and then you cannot cover the total. But how do you argue with that? Because the hardest problems in mathematics are to prove that something cannot be done. Because people can try things in many different ways, and how you deny all their possible attempts. There are exponentially many of those. So how do you deny them all? Eric, what's the argument?
No idea.
Oh, I thought you...
What if you stood the dominoes up?
Again, if you make them up, what
I
happens?
think you could cover
No,
it.
however you want. However you want. You can change.
No,
Look
like
it down, look it down.
Yeah,
If you go up,
vertically.
you will be okay with those guys. But here there are 7, there will be corner left here and corner left here.
You mean like in the Z?
Was
the
it?
Z direction.
Like coming out from the
Instead
board.
of
Both corners are the same color.
Very nice. Even if the board doesn't have to be chessboard, just if it's any board, you can color it. And how do you color it? So there are 8 lines. You start with black here, agree? And then goes black, white, black, white. At the end you have black, and this corner is white. Is that clear? And then what? Next line tries the other way. Tries black, goes white, black, and here will be white, here will be black. Is that clear? So this line starts with black, ends with white. Even, that's all odd ones. Odd ones start with black, end with white. And even columns, the other way around. Start with white and end with black. Is that okay? This is the 8th one. So what is the 8th pattern? Start with what?
Black.
No, that's like second. First and 7th will do that. 7th will start with black, but 8 will start with what?
White.
White and end with what? Black. And then what happens? When you do the cutting, you cut both black field, agree? So what are you left with? Out of 62 fields, 30 are black and 32 are white. Do you agree with me? And what happens? Domino, whether you put it vertical or horizontal, always covers what? One white and one black. So every coverage you might do will cover equal number of whites and blacks. Do you have equal number of whites and blacks? You can never have a coverage. Clear? So why did I put it in the pigeonhole principle? We can say, because what? If you want to cover everything, you must use 31 dominoes, do you agree? But then what? If you want 31 dominoes to cover 30 blacks, should then 2 dominoes cover the same black twice? And that's pigeonhole principle, and that's contradictory with this assumption. So that's a nice standard one. And there's a whole line of problems. What do you have? 3 by 1 dominoes in this configuration. There's lots of those problems of that type. It's surprisingly simple and surprisingly hard to imagine. Usually we all learn it, someone we read it and we get surprised. All right. Any other questions? If not, then let's
Question.
go to yes.
Number 6.
Number 6, what happens here? Oh, number 6 is basically the same one the longest sequence that's increasing. If they are all less than n, it will be n plus 1 decreasing. Just repeat the same, trading one of those n's in this group by n. Exactly the same. It's more like exercise if you understood that. Good. So let's go to section 3.5. What happens in section 3.5? Generally, 3.5 probably shouldn't even be there. 3.5 belongs more to chapter 5, but why did I put it there then? Because we need for 3.6. 3.6 is very important. Last section in this chapter is about mathematical induction. And that's one of the most important topics in our class. But then there are little ambiguous things about notation, and we wanted to fix that notation before we address the issue. So more serious discussion about sequences comes in chapter 5. This is like as much as we need to have so that our discussion on Wednesday is smooth. All right, so if something pieces are missing, that should be surprising. And as I said, it should be all there. For today, section 3.5 is sequences and summation. Those of you that already passed Calculus 2 remember maybe that topic as the beginning of chapter 9. We talk about sequences, although there we talk about infinite sequences. And then we talk about partial sums, and then we take their limits and do the conversion. And actually, if our curriculum, but you cannot always streamline curriculum, you should can actually first learn this before getting into calculus.
Thank you. Probably would have helped my students.
All right. So what do we describe as a sequence? As I said, sequences here will be finite. So what I wrote here is one finite sequence, and I wanted immediately to mention something that you don't always start with A0 or A1 as we very often do, because that's how we relabel the members. It might be that your calculation and process want you to label the first member of the sequence with AM and the last one with AN. So first term is AN is the initial term, and then AN is the terminal or the last term. Okay? What then? It's very important that we distinguish between M and AM. What is M? Or this I. I is the index that tells you the label or a rank of the member. What about AI is the value. So generally, lower index tells you about position, and then the whole thing AI tells you about the value at that position. So here it is. Here in example 351, I wanted to make sure that we understand if we have a sequence AN equals 3 to the n plus 5. So what is this formula telling us? It is called explicit because if I ask you how much is, in that problem I ask you first 4 terms, doesn't matter. Can I get 5th term right there, yes or no? And that's what explicit gives you. Gives you the opportunity to just calculate the number you need. You don't need the previous numbers. So what would that be? You recognize the value of n to use, and you get 3 to the 5 plus 5. By the way, can we think of a sequence as a function, yes or no?
Yeah.
But what is the domain of that function? It's not real numbers, but natural numbers, because you don't plug 1.5. You don't have 1 in the first member, agree? Unless you're doing factorial. But this is all from our DE class earlier today. So, so you plug in 1, plug in 2, plug in 3, and so on. And generally, that's why your domain are natural numbers. And your range are any number, real 1, or maybe even complex number, and so on. All right? Then in example 2, I ask you something that's, I don't know how important that is, but sometimes you get a sequence, and then you want to recognize the pattern, and that's what they ask you sometimes in calculus 2. So you want to recognize the formula, and that will describe that sequence. Can we do that? Okay. Problem number 352. We have the following sequence: -1, 1/2, -1/3, 1/4, -1/5, and so on. Can we write a general formula for this? And then actually what I didn't do there in my notes, I did the infinite one. That's okay, it will better connect to calculus 2. So if I want the infinite one, then what should I do first? I should kind of recognize how my and, how the value depends on the position. And then I record everything that's relevant. What is the first thing? First thing is I see how it alternates. You see this minus, plus, minus, plus? And if you remember from calculus 2, you usually take care of that by doing the alternator, we call it, and that is -1 to the n. Okay? So I'll write it like this. -1 to the n, and then that -1 to the n, when n is even, will make a plus. When n is odd, will make a minus. Although I don't like my alternator at this point. Why? Because sometimes you want to start on plus and go with minuses, or start with minus and go with the pluses. So sometimes it's n, sometimes it's n minus 1. How do I know? I just test it on the first one, and if it's not good, I take the other one. Let me see if it was good the way I started it. So if I want this to be my first number, -1 to the first, would that produce a negative?
For our terms, are we starting with the nth term or the first term? I mean, the 0th term or the first term? Or nth or?
In mathematics, we do both, so it's up to you. So generally, just make it sure that that's clear. For example, here I'll just start with A1, A2, but as I said, you can start with A minus 7 if you want. That's absolutely legitimate. So here it is. So I want -1 to the n, and then I'd like this to be A1, I want this to be A2, this would be A3, A4, A5, and so on. So what do we recognize immediately? Besides alternation, what else do I see? The numerator is always 1, agree? And then denominator always matches your index. If it's 5th member, it's 5. If it's 4th, it's 4. So if it's nth member, it's what? 1/4. Here it is. Then you test a couple of numbers and get it. As I said, recognizing the pattern is not official. I cannot even formulate it mathematically precisely, because can I make the other formula that matches the same description? Probably yes, maybe formula. But this is like for practical purposes, the simplest possible formula is probably this. All right, there are a couple of other skills that we need to learn about the series. So here's summation now. It's a little more complicated. So here's the symbol for summation. Again, finite summation. So it's not infinite summation, because infinite summation includes the limit. Here, I don't need the limit. So here's what we want to recognize. The following operation. Sum I goes from 1 to n, a I. symbol represents a number, really. And how do I get that number? First, I read the starting value and the ending value, and they produce the members of the sequence. It said starts means this. Produce A1 that starts on the bottom. And then produce all the members until you reach n. So produce A3, A4, and in the end you get A. Did I produce all members? Those indexes, lower limit and upper limit are telling me where to start and where to end. And then this symbol tells me what to do with them. Add them up. I cannot resist not to make a comment here. We are basically not ready for this definition. A real definition will come in that chapter 5. What's wrong here? What do these dots mean? How many numbers do we know how to add? We only know how to add how many numbers? 2. If you give me 2 numbers, I'll put them in the machine that we studied, and the machine will add them up. You read? If you give me 3 numbers, can I add them?
That's the first 2.
2 at a time, yes. What is this? This says what? Add first 2, and then add the third one, and then add again, and then how many times? Until you run out of members, really. But that's a strange construction. So it keeps things ambiguous. If you tell me 5 numbers, I'm okay. I'll say first 2, once again, third one, fourth one, fifth one, that's clearly function. But then, the longer the sequence gets, the more additions I have to do, agree? And that's where actually that becomes recursive, but we all understand what this means, agree? We have good intuition, so nobody objects. So here it is. If I say sum of 1 over 2 to the I when I goes from 0 to 3, do we all understand what that represents? That means I plug in 0 for I plug 1, keep plugging 2, 3. When I plug in 3, I reach my upper limit, I stop it there, I add them up, and I get the result. Alright? Here's my question. And this is one of the main reasons I want you to see this section before we do the induction, because we'll work a lot with these sequences like this. And I want you to avoid a common problem that people have, and it's like this. Sum. I go from 0 to n. 1 over 2 to the I. Do we all know what this represents? Yes or no? What is this? It's 1 over 2 to the 0, plus 1 over 2 to the 1, plus 1 over 2 to the square, plus 1, plus 1 over 2 to the 1. Is that what this represents? By the way I wrote it, this is not enough. Why not? Because this n is undisclosed, so this is in a way function of n, do you agree? And by the way, so this function is function of what? Is this function of I or function of n? Does this remind you of something? You remember second fundamental theorem of calculus? If you get integral from 0 to x, 1 to x, 1 over t squared dt. Is this function of t or function of x? Oh, no, because t just, is this function at all? Here's your t acting in full size. Is this function or is it a number? So your t at the end just ends in that summation, doesn't appear at the end. And then what? If I allow it to write to 17, what happens with that number? Will you get bigger number? So if I put x, who changes the value? Your t or my x? So this function of x. And second fundamental theorem of calculus tells you the derivative of that function is 1 over x squared. Remember that? Just plug in the upper limit and get it done. So, to connect again with what we studied in chapter 2, a variable t is what we call bounded variable, like every x. You don't plug it in, you just check all the domains. What about x? Is x 0, I already reached my 2 to the n. So in that case, this guy and this guy are not separate guys, really. It just tells you cut it right there. So how much is s of 0? Just what? 1 over 2 to the 0. Is that clear to everybody? As I said, this will be very important when we check some statements on Wednesday. So I want to make sure that we don't mess this up. So generally, instruction, don't think of this as the real object of learning. Think of this as instruction. Think of it more this way. Start with 0, stop when you reach 0, but then just do that 0 and don't do anything else. So that would be all of this. Just 1 over 2 to the 0. This is trivial observation, but as I said, I see it often as an error. That's why I want to do that. What's there? Again, little technical exercise. What did I ask you to do here? To recognize these expressions, to recognize their pattern, and to write them in sigma notation. Can you do that? So which problem is that? 355. So 355, what do we have? We have 2 squared minus 1 plus 3 squared minus 1 plus 4 squared minus 1. Let me write this in sigma notation. How do we do that? First, we recognize those pluses, so here are your 3 terms, 3 members of the sequence, and among them goes summation. What then? I recognize the pattern of each member. What would be, so what? This is 2 squared minus 1, this is 3 squared minus 1. Do I always have square minus 1? Yes or no?
Yeah.
So it's square minus 1. Who am I squaring? Goes 2, 3, 4. I can just call that I and say I squared minus 1. Agree? With my first I, 2. With my last I, 4. But someone can say, I don't like sequences that start with 2. I'd like it to start with 1. Is that okay? Yes, but then how can you rewrite it? Or
I minus y
you can
inside.
say the following. If I want this to be A1 and this is A2 and this is A3, then it's obvious that your base is always 1 more than the index, agree? So that will be what then? I plus 1 squared minus 1. Now your I goes for what? 2. Is that the same thing? Yes, if you plug it in, you will get it. Actually, what happened here is one very important technique that we use, again, in both calculus 2, we use the Kelvin differential equation when we solve the differential equations and everything, and that's called shifting the index of summation. Let's look what happened here. Just compare what happened here. Can someone comment when you see left and when you see right? What happened from left to right? I became what? I plus 1, agree? So I kind of pushed I by 1 up. What happened with the limits? Did they go up or they went down? Down. So that's how shifting goes. So variable up by k by 2. Then why do we make it ambiguous? Then what? Limits? Down by 2. So that's shifting the index. Actually, what happened here, we can explain it in a more sophisticated way. Why? Because here it is. Sum of I plus 1 squared. Here's how I can transfer this into this. Instead of saying, oh, if I go from right to left, what does that do with variable? Up or down? Down, and index is up. Always the opposite. If you don't like those ad hoc rules, maybe you prefer techniques of calculus 2, which is what? Substitution. So if I do the substitution, I'll say the following. Let me take J to be I plus 1. And do you remember how you change the variable in the integral? So it will be what? Summation. It's not I plus 1 squared. It's now what? Minus 1. And now, when you change a variable, you have to change the limit. What is the lower limit for I? 1. So when I plug it in, J will be 1 plus 1. That's 2. So J goes from 2. When I is 3, that was I plus That is, when you have definite integrals, once you change variable, you don't go back to substitute back because now you have your new limits. Just keep in mind to adjust the limits. So how you call limits, how you call variable on the definite integral doesn't matter at all. You can call it x, y, z. At the end of the day, you just plug in the limit in it, no matter how you call it. The same thing here. What is the meaning of this? Whether you call it j or I. Take numbers 2, 3, and 4, square them and subtract 1. What about this one? Is that the same thing? Does it matter how you call it? No. So remember that bounded variable under summation, you can change the name whenever you want. Of course, you're not allowed, if it appears somewhere else, to use a reserved name already, but generally this. As I said, either if you prefer to have more organized work, maybe you prefer to see a variable, or remember that shifting rule. That's useful. So let's see a couple of applications of this. I'll go back to some possibilities. Example 9. Says the following. We are doing sigma k plus 3 to 10 k over k squared plus 4. And I don't like to start from 3, I want to start from 0. Can we do that? So they said a right summation when k goes from 0. So if I want that index to go 3 down, then upper index will go what? But now, since my index went down, what happens with the variable, up or down?
Up.
So k will be replaced by what? On the bottom? K plus 3 squared plus 4 theta. And you say, is this really the same thing? Just to check your work. When I plug in first lowest limit, what do I get? 3 over 3 squared plus 4. Agree? When I plug in my 0, what do I get? Over. Do I get the same thing? Yes, you are just, your counter is different, and your expression is different, but the values are the same. As I said, this is helpful in certain situations, and I'll show you one of them immediately. What happens here? I want to add up two sums, finite sums, that have a different do they have the same limits or different limits? Oh, that's easy. I don't have to do anything. It doesn't work out, but let's do it. So what do we have in 3, 5, 10? It says 2 times the sum of 3k squared plus 4 when k equals 1 and plus 5 times sum k equals 1 and over 2k squared plus 1. Can we combine these two series? Yes or no? Yes.
So you used it in the paper, but you want to use explicitly parentheses or something to indicate that we're taking the sum of 3k squared plus 4. So when you read that,
I
yeah.
agree.
but that's just so people
Yeah,
understand.
sometimes, yes, people kind of think which one is it, and really, I absolutely agree with Bryce's comment. Most often, people might think that 4 is outside of it, and it's not part of any thank you.
Judge.
Oh, yes, I had part of
Yeah.
that was much better, yeah. So what happens now? Generally, what I'm doing is the following. If you think what's behind this is that if you write your n members here, and then your n members here, you are using commutative laws, and you combine first with the first, second with the second, and you are building them together. So that's what you are doing in a generic way. So what we do, take a generic member from here, and end up with a generic member from here, but of course you have to combine these 2 and 5. So what can I do with 2?
Take them inside.
Okay, get it inside, what am I doing? Using distributive law. Because this is the sum, so you can double everybody. What do I get? 6k squared plus k. once, and you just say how often do you repeat it. So here it is. Here's my arbitrary number. Here's my arbitrary number. Well, I'll just add those generic numbers. So 6k squared plus 8 plus 10k squared minus 5. And I get my sum will be what? Can I combine the like terms?
Yeah.
And the business is 16k squared plus 2. Did I get a nice finite series again? Yes, and then if you give n, I can just produce all the members. And so from the format of the series, I got again the format of the series. And that's very successful. And then what can happen? It can happen that we're very lucky here that everything matched. Index is matched, and sometimes they don't match. And then what you do, yes, you have different options basically. So here's another example. 511. What we have to do is sum k equals 2 to 10. 2k plus 1 plus sum of k minus 2 when k goes 1 to 9. We did something like this in our differential equation class recently. But what happened there, I was less concerned about the indexes because in that class, just a little side comment. I had some x to the k and here x to the k plus 1 maybe. And in that class, I said, oh, I don't care about indexes as long as powers of x match. And that's where I paid the price and shifting always to make x's to be alike terms. For us here, we don't have to do that. So my question is, how can I add them up?
Shift one.
Although, you don't have to, why would you shift the index? I don't, this is fairly easy, like cherries, you can do whatever you want to do. But, let me warn you, sometimes, for some reason, like the one that I mentioned in my DE class, you don't want to shift indexes, because that will ruin something else, maybe. So can I add them the way they are? What? Here it is. What is their overlap? Everybody has members between second and 9, you agree? Does this guy have an extra member at the end?
Yeah.
Does this guy have an extra member at the beginning?
Yeah.
Separate them and keep them on the side. So here's how I can do it. I say the following. I say sum k goes 2 to 9, 2k plus 1, and plus 21. How did I get this 21? I just calculated the 10th member. Is that okay with everybody? What did I do now? Plus, now I want k also from 2 to 9. And whoever is extra, I'll calculate. How much is my extra? Negative 1. Because k was 1, I don't need it. So plus 1 minus 2. Now, do they match nicely? Yes or no? So do I get sum? When k equals 2 to 9, 2k and k is 3k minus 1. What about extra member? 21 minus 1, that's 20. Does this look good? If you don't like to have a member here that stands so much, maybe we can push it in and call it, that's my first member and piecewise function. But as I said, usually for most of the constructions, this is just completely nice. Because sometimes I ask the question, write it as a single sum. Is this single sum or two sums? In a way, but as I said, I should call this as A1 and then add it as a single sum. But this is always tolerable as a single sum. Extra constant. But what is the other way? The one that I probably did in the notes. What is the alternative? May I raise this? If I'm allowed, and if it doesn't harm anything, can I shift one of them so that they both become 1 to 9? Yes or no?
Yes.
Then that's a different story. It would be what? K goes from 1 to 9. 1, then since you're doubling, what do you get? 2k plus 2 plus sum k goes 1 to 9, k minus 2, and then what? Sum k goes 1 to 9, 2k and k is 3k, does it look nicer? Yes, it does, as I said. My warning a minute ago was just maybe you cannot always afford this luxury, and then, having a standing member doesn't work. Yes.
So if the ranges aren't equal, so from 2 to 10 and 2 to 8, we can still split off 2 from
Exactly.
and
You
then-
have to. In that case, there's no shifting that will make them equal length.
Yep.
Exactly. But first technique then tells you, put on the side whatever's extra, and then whether shift or not. Look at the context. That's it. This is general construction, and sometimes it's better to do it one way, sometimes it's better to do it the other way. All right. Generally, I would say that's what I told you. It's going to be fairly simple. Oh no, there was one thing I forgot. What did I forget? In the middle of the section, there is another notation that you maybe haven't seen before, and that's called product notation. And you usually use that in calculus too. The same way as you have sigma notation, can you introduce the product notation? Yes or no? How would that work? The same way. You just have product contained recursively. I equals 1 to n. It's just a1 times a2 times a3 times n. And then what? So those products then are also interesting. My question is, how comes that you didn't study those products in calculus 2? For convergence, for all that. You only studied sums. Are sums really that much more important than products? Here's one of the reasons. Products are sometimes nice to express some things. There is lots of presence of products in calculus or mathematical analysis. But here's the thing that actually helps you to avoid products very often if you don't have that machinery. Here's what you do. If I have a product, then what can I do? I can take the following. I take ln of that product. So it will be ln of a1, a2, an. And that becomes ln a1 plus ln a2 plus ln of an. So then call them b1 and b2. And now your product became what? A sum. So, for example, can someone tell me what is the necessary condition for a convergence of a product? You remember there was condition for, what is necessary condition for convergence of a sum? That individual members must approach what? 0. Remember that? We call it divergence test or member test or however you call it. So it says, so for a product, what is divergence test? If you want product to diverge, to converge, then what? Product must approach sum A. When you take ln, sums has to converge. So sum of bi has to converge. So is it true that bn should go approach 0? Yes or no? But what is bn? Bn is ln of an approaches 0. An approaches b to the 0, which is what? 1. Products converge only if the members approach infinite product, if the members approach 1. Because 1 times 1 times 1, that stays under control. Like 1.3 times 1.3, that's too much. Or if you take 0.7 times 0.7 times, that's obviously approaching 0. That's trivial. So generally, the main battle is around 1, the same way as the battle is around 0 for sums. So that's how you can connect product and sums. And usually they think in your curriculum, if you learn sums, then you can easily kind of pick up products whenever needed. But products are very good for some nice representation of functions. For example, gamma function has also nice representation of the product.
actually recently just encountered an infinite product of integrals. You know, they're Feynman path integrals. Really cool stuff. That's what
Very good. All right. So what's the plan? Let's recall once again. So on my side, I'm supposed to post another analytic test, so if you want to practice more. What else? I will report, I will take your quizzes if you want to use them to improve some old scores. On Wednesday, we have another quiz that will be similar to the one that we didn't count. So we now want to do better. Again, I'll give you two sets. First, to kind of do product or intersection or something like that. And the second one, prove, either by element or argument or by sense. And then